It is time to follow along now from the notes packet. We are looking at Part 1, Infinite Integration Limits, Example A. In Example A, it is the integral from 0 to infinity e to the negative 2x dx. We saw this in the introduction. In each problem, you are required to use the definition of the improper integral. If you recall, it's a limit statement. So this one is going to be the limit as, well, not say as yet, but from 0 to some bound b, e to the negative 2x dx. And we want to find what is the limit as that bound b approaches infinity. From here, we're just going to use some good old-fashioned integration techniques together with the limits. So this is the limit as b goes to infinity. We don't want to drop that from our statement. And the antiderivative then becomes e to the negative 2, e to the negative 2x. Of course, this would result in a negative 1/2 being pulled out in front with a u substitution, and that's going to go from 0 to b. So that's just standard notation for the fundamental theorem of calculus part 2. Now, as this continues, I'm going to pull the negative 1/2 out. This makes it a little less clunky, times the limit as b goes to infinity. Now I employ the fundamental theorem of calculus, part 2. So I'm going to take and plug in the b into the expression, minus, and I'm going to take in and plug in the 0. Of course, this expression will go to 1, while this one here will go to 0. So then this is going to be negative 1/2 times a negative 1. So the answer to this problem is 1/2. Remember, this is a limit. The limit equals 1/2. Now, if you're going to think of this in terms of a geometric expression, let's take a look at this curve. I'll do this in a yellow color. This curve here, a decay function. Let's say that that curve there is y equals e to the negative 2x. And suppose we tried to translate this integral into a geometric expression, maybe the area under the curve from 0 all the way out to infinity. Well, if I were to look at this area, since this is asymptotic and never touches, one could argue that the area diverges. It never comes to a value, it continues to grow. But we say in this case that that area converges to 1/2. A similar argument is made in infinite geometric series, where you say 1 plus 1/2 plus 1/4 plus etc., etc., etc. Now you should know from an earlier course that this sum is going to equal the first term 1 over 1 minus the common ratio, which is 1/2. So then this is going to come out to be 1 over 1/2, or simply 2. So the argument is, well, if we're adding on these small fractions infinitely, well, won't the sum continue to grow? But you've learned from a previous course that that sum converges to 2, which is a similar argument here, that the sum or the area is converging to 1/2. Example B, the integral from 0 to infinity of x squared dx. So if I use my definition here, this is the limit as b goes to infinity, the integral from 0 to b, x squared dx. Now I'm going to go through the process again. This is going to be the limit as b goes to infinity, the antiderivative x cubed over 3, and we will take that from 0 to b. I'm pulling out the 1/3 limit as b goes to infinity. Let's be a little more careful there. B goes to infinity. I'm going to plug in the b cubed, and I'm going to plug in the 0 cubed. This, of course, is equal to 0. but this then is going to go to infinity. So we're going to say here that this entire limit does not exist. It grows without bound. We would say in this case that it diverges. It does not converge. It diverges. It grows without bound. Now this is real easy to see in the geometric sense. If I take a look at that curve, let's say y equals x squared, and that's going to be this parabola. And if I look at the area under the curve from 0 to infinity, well, we see that that area keeps growing and growing and never stops growing. It grows without bound. We say that the area diverges. Example C, this one is from negative infinity to 1, e to the x dx. So we're going to use limit definition, the limit. Now this time, the bound that is not defined is the bottom bound, and I like to use the marker A for the bottom bound. That's my preference. You can use any marker you'd like. And so now this is the limit as A approaches negative infinity. That's our limit statement that we desire. So let's go through here. So this is going to be the limit as A approaches negative infinity. Our antiderivative, easy enough, e to the x, and that's going to go from A to 1. So then this equals the limit as A goes to negative infinity. Please carry the limit statement each time so to avoid errors. And this is going to be e to the 1 minus e to the a. Alright, so what does this? We certainly see that it's e to the 1 is e. E to the a, where a is approaching negative infinity, that's clearly going to equal 0. So then we say that the limit equals the value e, which is pretty darn fascinating if you ask me. So let's take a look at the graph. And the graph here of e to the x is a growth function. Looks like that. And y equals e to the x. But what we're looking here is as we come from negative infinity up to value of 1, here, let's say 1 is here, then again we're saying that that area converges to E. Pretty ambiguous concept here. Arguments could be made and fights could be had about what do you mean an area converges. Again, the one thing I can tell you is think of infinite series. A similar kind of logic is had there to make sense of this. Now for example D, the final example of part 1. This one's kind of fun. Not kind of, this one's really fun. We have two bounds, both of them are undefined. So the first thing I'm going to do, so that I have something defined, I'm going to break this up to any number that I want. I'm going to choose the number 0. So from negative infinity to 0, 1 over 1 plus x squared dx, plus the integral from 0 to infinity, 1 over 1 plus x squared dx. Now for this problem, what I'd like to do is first look at a graph. Okay, in this graph here of y equals 1 over 1 plus x squared, that is going to have this shape here. It is a bell shape. It's not the bell curve, not the normal curve, but it is a bell-shaped curve that looks like this. So the question becomes, will this area here converge? Now just because it's approaching this asymptote does not necessarily mean that the area is going to converge, and we'll discover whether it does or does not in a moment. So the property that I wanted to point out about this function is that it's an even function. It is symmetric about the y-axis. So what we need to do is really find one of them. So I'm going to work with the positive infinity. I find that's just a little easier to do limit statements with. And if this, let's say, goes to infinity, then the whole thing is going to diverge. If this goes to a real number, then the area is just twice that real number. So I'm ready to begin. So we're going to look at this integral here alone. The integral from 0 to infinity, 1 over 1 plus x squared dx. Alright, we're going to use definition. Limit b goes to infinity. Integral from 0 to b, 1 over 1 plus x squared dx. Next, limit b goes to infinity. We need the antiderivative of 1 over 1 plus x squared. Oh boy, I hope you memorize this. It's an important one. This is the inverse tangent of x as the antiderivative. And of course, we're going to take that from 0 to b. So next, we're left with the limit as b goes to infinity. Inverse tangent of b minus the inverse tangent of 0. Now from your pre-calculus class, you should have a working knowledge of the graph of the inverse tangent. It will help you in this problem. The inverse tangent does this here. It approaches an asymptote, top and bottom. So question is, what is that asymptote? So here, this equals the inverse tangent of b as b approaches infinity. So as x increases or b increases, the function is going to approach the asymptote of pi over 2. So this is going to approach pi over 2, while the inverse tangent of 0 is simply 0. So that means, now remember this is only half of it, that means that this area to the right converges to pi over 2, and then it means above here, I kind of got my own way, this is going to equal this here, this expression is going to be 2 times pi over 2, or simply pi. Isn't that crazy? I find that to be absolutely amazing that the area under this particular curve is equal to pi. Sweet.